Hi everyone, in this video I'm going to show what is this time domain analysis. What do we analyze usually on the time domain step response of a closed loop unity feedback. And from here we look at what are the criteria or the specification that we look for in this output. Normally we will actually assume a closed loop system of something like this, where we have a forward transfer function normally labeled as G, and we have a sum. Okay, so minus here means that we are taking the negative feedback from the output. So let's do some labeling over here. So as usual, we will be labeling the output as our YS and the input as the US. Okay, so and as overall, the entire closed loop systems, okay, in this red box, we are going to label it as TS. So this will form our entire systems, and then the one showing here will be our step response. So taking the normal case here, we will be actually taking input as a unit step input. So unit step input UT versus T, and the input will be just one straight line with an amplitude of 1. So by supplying this input, okay, which starts at T equals to 0, we have an input of 1 supplied into a closed loop feedback with a unity negative feedbacks ratio over here. This one is 1. Okay, and we will produce output of something like this. What are we actually trying to look at here? It is that we are trying to give a label to the system, whether is it fast, whether is it stable, or whether is it accurate. To do this, we are going to define a certain criteria, okay, in labeling the performance of the systems. Generally, we are looking at 3 things. One will be the transient, steady state, and finally stability. So what do I mean by transient at the first place over here? So transients and steady states tells the time domain output, separates the time domain output into 2 sections. So we keep break this part into 2 sides, and the one on the left before the systems get steadied will be the transient, and after that the system will be steady. So, and a transient usually we are going to measure in a few items. So first one is our settling time, TS, and then we have a rise time, and we have our maximum overshoot. As for steady states, we'll be interested in the steady state error, and the stability we are looking at the absolute and relative stability. So this will be the key terms to define the performance of a system in its time domain output. Okay, so let's look at the transient. So what do we look for in a transient? So transient, we have again steady state, rise time, and maximum overshoot. So what do you mean by the settling time? So the settling time is the time needed for the system to settle. Therefore, the name called settling time. So how do we define that? Is that we actually following using the 2% criterion. So 2% criterion is that we are looking at the final value of the system, and we are looking at these 2 boundaries. So the upper boundaries will be the plus 2%, and the lower boundary will be the minus 2%. And the time needed for the system to settle within this range will be called the settling time. And as for the rise time, we are looking at the time needed for the system to rise from 10% to 90% of its final value. So this is T10, this is T90. So the difference between the two will be our rise time. So I repeat again over here. So this is 90% and this part will be the 10%. Somewhere around here, as I mentioned, when you reach to here, somewhat around this time will be our settling time. And the maximum overshoot will be the highest point from its final value. So from here to here will be our maximum overshoot, and we normally measure in terms of percentage. These three criteria here will be the specification that we actually look at. Okay, when we actually try to design a control system, or we want to measure the performance in their transient. So we normally look at settling time, rise time, and maximum overshoot. As for the steady states, we are looking at the difference between the final output and compared to this set point. Set point means here. So this is my set point, or my input basically. And the set point ut approaches infinity is 1. So at this point, my yt approaches infinity is 1. So what will be my ESS, steady state error, will be the difference between the output at infinity minus the set point towards infinity divided by the set point towards infinity multiplied with 100%. So that gives us a steady state error. So in this case here, if your final value of your set point is 1 and the final value of your output is also 1, that means your system actually returns with no steady state error. And lastly, for our stability here, we are looking at two criteria. One is the absolute, another one is the relative. Basically, it means pretty much the same thing, but absolute tells you whether it's yes or no, whether it's stable or not stable. And relative stability means that it's how much the system can sustain before it reaches instability. In this example, if you look at here, basically the concept of the stability is bounded input, bounded output. As long as your input is bounded within a certain region, and your output is also act accordingly without exceeding a bounded region, that means your system will be deemed as stable. In this case here, we can see that the system actually initially goes up and then finally it returns to equilibrium states. That means it's within the bounded region, and hence we can say the system is stable. Basically, just to repeat, if you want to look at the performance of a system in its transient, basically we are looking at the transient. We also look at the steady state, and finally we look at the stability of the system. Okay, so thank you for watching.